Okay, PDE. So today is scheduled as a review for the exam. So I'm happy to answer questions, and if there are not any questions, then I'll just start going over some problems on ordinary differential equations to kind of survey everything that we've done so far. So, are there any questions? Anything, problems you would like me to do, questions to go over? Or anything in the lectures or in the text?
Hi, Professor. From the homework 6, can you do the number 14? Page 319.
Okay, let me look it up. All right, so this is on page 339. Is that correct?
319.
319, okay, and which number?
This is 14.
Number 14?
Yeah, number 14.
Okay.
It's about the Grove's law for the census. It's like 4 problems, but this is I need to know how to tackle.
Okay, so number 14 refers to number 13. And so this is on population growth. So let me take a look and see. What it is. So the idea is that we approximate or we model population growth by a function where the rate of growth is proportional to the population. And so so this is our usual exponential growth function. dx dt is some constant times x. And in some cases, k depends on t. But what often happens in a very simple model where the population is growing exponentially, but let's say you think of this maybe as you put some rabbits on a desert island and the population starts to grow, but there's a limit to how many rabbits the island can sustain. There's only so much vegetation. So at some point, the population growth slows down, and it may still be increasing, but more and more slowly and approaching some maximum. And so if you think of the idea where you have a maximum population of m, then dx dt, in the beginning, it's proportional to x, but after a while, there's also a factor of m minus x. As you get closer and closer to the maximum, you end up with an equation, a model that looks like this. And So this is an equation that you might have seen in calculus, in first year calculus. In the second semester, at least at Lehman, we have, there's a section on differential equations in the syllabus. And one equation you can try and solve is this equation. So let's start with number 13, which is to solve this equation. Okay. So the x dt is kx times m minus x. And what kind of equation is this? This is separable because you have on the right-hand side a function of x and a function of t. The function of t is just 1. So if we separate this, we would get, let's say, 1 over x times m minus x dx dt equals k. Or the integral of 1 over x times m minus x dx is the integral of k dt. And can we do these integrals? Well, of course, on the right-hand side, this is just kt plus a constant. And on this side, we can solve this using partial fractions. Okay. So is there any question about how I got from here to here? This is my differential equation. It's sometimes called the logistic equation. Of course, it's a model for many, many situations, not just population growth. And how do we do the integral on the left? So we have 1 over x times m minus x. This should be equal to something over m minus x and something over x. If I were to add these, I would get x plus m minus x over m minus x times x, which is m over m minus x times x, which means if I divide by m, I get exactly what I want. So the integral of 1 over x times m minus x is 1 over m times the integral of 1 over m minus x plus 1 over x dx. This is, what's the integral of 1 over 1 minus x? It's minus the log of m minus x. And the integral of 1 over x is the log of x. So this is equal to 1 over m times the log of x over m minus x. All right. So let's see. So when we have our logistic equation, or the equation dx dt equals kx times m minus x, when we separated the variables, what we get is that the integral of 1 over x times m minus x is the integral of k dt, which is kt plus a constant. And this is 1 over m times the log of x over m minus x. Are there any questions about this? So let me try and solve this equation for x. So how should we do that? So 1 over m times the log of x over m minus x is minus 1 over m times the log of m minus x over x. This minus 1 is just the reciprocal. So this is minus 1 over m times the log of m over x minus 1 equals kt plus c. So the log of m over x minus 1 is equal to minus k over mt plus a constant. So m over x minus 1 is e to the minus k over mt times e to some constant. I'll just write this like this. So m over x is equal to 1 plus c e to the minus kt over m. So x is m, I'm just taking the reciprocals, times over 1 plus c e to the minus kt over m. So this is the solution of this population growth equation. And so I guess following the problem in the text, number 13, that T1 be the time when you've gotten to half of the maximum capacity, when x equals m over 2. So let's see if we can use that to calculate the constant c. We get m over 2 is equal to m over 1 plus c e to the minus k t1 over m. When t equals t1, x is m over 2. So the m's cancel. Let's just write this as, if you take the reciprocals, 1 plus c e to the minus k t1 over m equals 2. So c e to the minus k t1 over m is 1. So e to the k t1 over m equals c. That's what c is. So x is equal to m over 1 plus e to the k t1 over m, e to the minus kt over m, which is m over 1 plus e to the minus k t minus t1 over m. And if we let alpha be equal to k over m, we get x is m over 1 plus e to the minus alpha t minus t1. So this is exactly equation 823 in the text. So this is solving this equation, which is a nice example of a separable equation. Right. Any questions about this? Okay, so this was number 13, which we needed to do in order to solve problem 14. So problem 14 says, assume the growth law in formula 8.23. So the population at time t is of the form m over 1 plus e to the minus alpha t minus t1. Right? So this is our growth law. And suppose a census is taken at 3 equally spaced times, resulting in the numbers x1, x2, x3. So we're told that x of at time t1 is x1, x of t2 is x2, x of t3 is x3, and these are equally spaced times. That means t1, t2, t3 equally spaced. T2 minus T1 is the same as T3 minus T2, right? That's what equally spaced means. And we want to use this to compute M, which is the maximum population that the environment can sustain. All right? All right. Any questions about any of this? Suppose I call this, just for in case I need it, delta t. That's the time interval from T1 to T2 and from T2 to T3. So we're told that x1 is, let me just use this for T1, why not? Let's see if it works. M over 1 plus e to the minus alpha times 0. Sorry, maybe that's not a good thing to do. So I'm going to take, so this is my law. X of t is m over, I don't want to use T1 because I'm going to use T1, T2, T3 here. So this is really 1 plus some constant times e to the minus alpha t. Okay. So x1 is m over 1 plus c e to the minus alpha t1. This is x at time t1. X at time t2 is x2. That's m over 1 plus c e to the minus alpha t1. but this is the same as m over 1 plus c e to the minus alpha. This should be a T2. T2 is T1 plus delta T. Let me just write this bigger, basically. M over 1 plus c e to the minus alpha T1 plus delta T, and x3 is m over 1 plus c e to the minus f of alpha 1, f of alpha times T3, right? T2 is T1 plus delta T. T3 is T1 plus 2 delta T. Right? So what I want to do is to somehow solve these equations for m. And I have 3 equations, and I should be able to eliminate some of these constants. So for example, so let me just try and work this out. I'm not sure how informative it is, but if we have m is equal to, we had m over 1 plus c e to the minus alpha T1 equals x1. So that means that 1 plus c e to the minus alpha T1 is equal to m over x1. So c e to the minus alpha T1 is m over x1 minus 1. X2 is equal to m over 1 plus c e to the minus alpha times T2, which is T1 plus delta T. So that's m over 1 plus c e to the minus alpha T1 times e to the minus alpha delta T. I know what this is. It's equal to that. So this is equal to m over 1 plus m over x1 minus 1 e to the minus alpha delta T. X3 is m over 1 plus c e to the minus alpha 1 alpha T1 plus 2 delta T times e to the minus 2 alpha delta T. Now, let me try and do it just slightly differently. So this is x3 is m over 1 plus c to the e1 e to the minus alpha T3. That's m over 1 plus c e to the minus alpha T1 plus 2 delta T. That's equal to m over 1 plus c e to the minus alpha T1 e to the minus 2 alpha delta t. We already saw what this is. I can replace this with this. This is m over one plus m over x1 minus 1 e to the minus 2 alpha delta t. All right. Well, actually, so I can see it just, oh, we've gotten to the point where it's just a lot of high school algebra. And, you know, I suspect it would take me a half an hour to work this out, but it's just doing high school algebra. We're not doing ordinary differential equations anymore. So it's worth doing, but it's not worth doing right now in this review session. The important thing is being able to solve the differential equation. So here is our differential equation for population growth, where there's a maximum carrying capacity of the environment, M, and this is a separable equation. We work it out, and we got the solution. This is really the important part of this, and that's as much as I'm going to do.
Okay, and the last one, Professor, the last one for me.
Which is the last one?
Yeah, I wanna you do the from page 339, number 7. Yeah, involved differential equation.
Okay.
Thank you.
Page 339, number 7. For a certain positive number k, the differential equation of simple harmonic motion, which is y double prime plus k squared y equals 0, has solutions of the form y equals f of x. So we have a solution, y equals f of x, with f of 0 and f of 3 equal to 0, and f prime of x negative for 0 less than x less than 3. Compute the constant k and find all solutions. So what we're told about this is whatever is the solution f of x has the following property. It's 0 at 0, it's 0 at 3, and it's strictly less than 0 between 0 and 3. So what can we say about the function? So if we look at y double prime plus k squared y equals 0, what is the general solution? It's y equals constant times, well, it's of the general form a times the sine of kx plus alpha, right? So every simple harmonic oscillator has a solution which can be represented in this form. It's a sinusoidal, it's a sine wave with amplitude a, and there's a phase shift of alpha. So what are we told? So this is my function f of x. So what is f of 0? F of 0 is a times the sine of alpha is equal to 0. And we know, first of all, that a is not 0, because if a were 0, this function would be identically 0, it would never be negative. So a is not 0. So f of 0 is a sine alpha is 0. That means that the sine of alpha is 0, which means what angles have alpha, what angles have sine 0? alpha is some multiple of pi. So it's k times pi for some integer k. What about f of 3? F of 3 is a times the sine of 3x plus alpha, and that's also 0. Which means, because a is not 0, the sine of 3x plus alpha is 0, which means that, f of 3 is 3k, and let x equal 3, I get 3k plus alpha. So the sine of 3k plus alpha is 0. So let's see, I can do this in a couple of different ways. Let me just use the addition formula for the sine. So the sine of 3k plus alpha, this is the sine of 3k cosine alpha plus cosine of 3k sine of alpha. Sine of alpha is 0. So this is the sine of 3k times the cosine of alpha. But alpha is a multiple of pi. And the cosine, so this is, I shouldn't have used a k here. Call this n, some n. So this is the sine of 3n times the cosine, sine of 3k, times the cosine of n pi. The cosine of n pi is minus 1 to the n. So this is minus 1 to the n times the cosine times the sine of 3k sine of 3k, that's 0, which means 3k is a multiple of pi. Sorry. Right, which means k is equal to n times pi over 3 for some n. So let me just repeat this analysis. It's interesting. We have our simple harmonic oscillator. We have a function y of x that satisfies this differential equation. And if a solution, we're looking for the particular solution f of x, where f of 0 equals 0, f of 3 equals 0, and between 0 and 3, this is negative. So we're told that we know the general solution is a sine of kx plus alpha for some constants, capital A and alpha. If we plug in x equals 0, we get a sine alpha, which is 0, which means the sine of alpha. So alpha is some multiple of pi. Right? These are the only angles whose sine is alpha. So alpha has to be a multiple of pi. What about when we let x equal 3? We also get 0. When x is 3, we get a times the sine of 3k plus alpha is 0. So a is non-zero, so the sine of 3k plus alpha is 0. If we just write down this according to the addition formula for the sine, it's not necessary, but it's perfectly nice. We get sine 3k cosine alpha plus cosine 3k sine alpha. But alpha is a multiple of pi, so sine of alpha is 0. So we just get this. And alpha is a multiple of pi, n times pi, that's minus 1 to the n. So the sine of 3k times plus or minus 1 is 0. So the sine of 3k has to be 0. So 3k is also a multiple of pi. So my frequency k, essentially a frequency k, is a multiple of pi over 3. Now, what can it be? We're looking at a sine function. F of x is a times the sine of kx plus alpha. It oscillates. If it's 0 at 0 and 0 at 3 and negative in between, that's half of the period. The other half of the period will be from 3 to 6. So a sine of kx plus alpha has period. What is the period? 2 pi over k equal to 6, which means k is equal to pi over 3. So that's what k has to be. So our function is f of x equals a times the sine of pi over 3x plus alpha. And alpha is a multiple of pi. It's either 0 or pi. So if we look at the function sine of pi over 3x, that's 0 at 0, it's 0 at 3, and in between is positive. If we look at the sine of pi over 3x plus pi, what does the graph of that looks like? It's 0 at 0, it's 0 at 3, and as x goes from 0 to 3, this goes from pi to 2 pi. The sine from pi to 2 pi is negative. So that's what it has to be. So our function f of x is a times the sine of pi over 3x plus pi. This is the solution of our problem. Let's see. In terms of how much work you have to do for a question on the exam, I'll be very explicit on when I state the questions.
Professor, for that problem, the -1 is indicate periodic, is a periodic function.
Wait, let me just add one, sorry, just one more thing. This is also the same as f of x equals minus a, assuming a is positive. This is minus a times the sine of pi over 3x. I'm sorry, and what are you asking? What is your question?
Yeah, you wrote on the paper an expression and involve -1. It's like a formula, which means it's a periodic.
Wait, are you talking about?
Yes, yes.
All right.
Right, the cosine n pi equals the periodic, yes.
Well, no. Cosine of n pi is just a number. It's plus or minus 1.
Yeah, the
depending
minus
on
1.
whether n is even or odd.
Yeah, but you wrote the -1 power n means it's periodic.
Well, no, there's no, it's just a number. Numbers aren't periodic. This is not a function. This is just or it's a function of n if you like, but it's just a number. If n is an even integer, this is +1. If n is an odd integer, this is -1. What's periodic is the solution of the differential equation. All right? This is our periodic solution. Every solution of this equation is periodic. It's a sine function.
Thank you.
Are there other problems you would like me to go over, or other questions that you might have?
Yes, homework 5, number 9.
On page 347?
Yes, 347. Thank you.
Are there other people who have questions? I mean, I'm happy to go over almost anything here. Okay, so page 347, number 9.
Number 9, yes.
So we have the following differential equation: x squared minus 4y prime equals y. Or I can write this as y prime equals 1 over x squared minus 4 times y. And in that form, we see that the equation is separable. So we can write 1 over y prime, or dy dx, equals 1 over x squared minus 4. So when we integrate, we get 1 over y dy is 1 over x squared minus 4 dx. And what we have on the left is the log of y. And x squared minus 4 is x minus 2 times x plus 2. And when it factors, we can use, again, partial fractions.
Professor, at that part, I use a trick substitution. The trick.
Sorry?
So you can use also the method too. That is wrong.
Well, I mean, 1 over x minus 2 times x plus 2 is the same as a fourth 1 over x minus 2 minus 1 over x plus 2. Right? That's the partial fraction expansion of this. And the 1/4 can come outside. We get 1/4 times the log of x minus 2 minus the log of x plus 2. So we have the log of y plus a constant equals 1/4 the log of x minus 2 over x plus 2 plus a constant. If I bring the 4 over to the left, I have the log, I have 4 log y, which is the same as the log of y to the 4th power, is the log of x minus 2 over x plus 2 plus a constant. So if I exponentiate, I get y to the 4th equals some constant times x minus 2 over x plus 2. Or you could also write it if you like, it really makes no difference, as x plus 2 times y to the 4th is some constant times x minus 2. So the solution of this differential equation is given implicitly in this way. Okay? Questions? Yes, no, good, bad? Okay. Anything else?
Professor, can you go over question 11 on page 333?
333, number 11. Okay. Let me look for it. So number 11 is y double prime plus y prime minus 2y equals e to the x plus e to the 2x. So there are
your camera's, oh, never mind.
okay. So how do we solve the a non-homogeneous equation like this? So find the general solution of the homogeneous equation, y double prime plus y prime minus 2y equals 0, and add a particular solution of the non-homogeneous equation. So for the homogeneous equation, it's a equals 1. Remember, the general form is y double prime plus ay prime plus by equals 0. So when we have y double prime plus y prime minus 2y equals 0, a is equal to 1, b is equal to -2. D is 4a minus b squared. That's 4 minus 4 is 0. Right? When D is 0, what does the solution look like? Oops, did I do this wrong? Oops, yeah, sorry. Let me do this correctly. That's always a good thing to do. A squared minus 4b is 1 squared minus 4 times minus 2 is 1 plus 8 is 9. So k, which is a half, the square root of d, is 1/2 the square root of 9, which is 3/2. So for the general solution, it's of the homogeneous equation, we take the two solutions, V1 and V2. V1 is equal to e to the minus a over 2. That's e to the minus x over 2 times e to the kx, e to the 3/2 x, which is e to the minus x. Oops, e to the plus x. Minus 1/2 plus 3/2, e to the x. And V2 is e to the minus x over 2, e to the minus 3/2, which is e to the minus 2x. So for the non-homogeneous equation, the general solution is some linear combination of V1 and V2. How do we find a solution to the, so general solution of the homogeneous equation, y double prime plus y prime minus 2y equals 0, is some constant times e to the x plus a constant times e to the minus 2x. Now, to find a particular solution, so I did not assign both the problems 9 and 10, but in problem 9, so problem 9 was to solve the equation y double prime plus y prime minus 2y equals e to the x. So suppose for that we had a solution, let's say u1 of x, or w1 of x, let's say, just to be safe. And for problem 10, that was y double prime plus y prime minus 2y equals e to the 2x. And let's say a solution of that was w2 of x. So if we had done both problems 9 and 10, then w1 of x plus w2 of x would be a particular solution of this equation star. Okay, so if I had assigned problems 9 and 10, or if you had chosen to do problems 9 and 10 separately, then you add those two solutions and you get a solution to this equation, right? Basically, because this is what's called a linear equation. And these two equations are easy to solve. You would just try a function of the form constant times e to the x, or e to the constant times x. No, constant times e to the x, or e to the 2x. But so this is one method. But let me solve it. So we will solve directly using the Wronskian. So the Wronskian W of my functions v1 and v2 is the determinant of the 2 by 2 matrix, which you get by writing v1 and v1 prime, v2 and v2 prime. So that's the determinant of what is v1? E to the x, and v2 is e to the minus 2x. The derivative of e to the x is e to the x. The derivative of e to the minus 2x is minus 2 e to the minus 2x. When I compute the derivative, I get minus 2 e to the minus x minus e to the minus x. This is minus 3 e to the minus x. Okay. All right. Is that okay so far?
Yeah.
Yes, yes.
Okay. So remember, particular solution, I need to find these functions that in the text are called T1 and T2. See, T1 of x is minus the integral of V2 of x, the Wronskian over R of x dx. R of x is the right-hand side of the equation. So this is, let's see, minus the integral. V2 is e to the minus 2x. The Wronskian is minus 3 e to the minus x. And the right-hand side of the equation, oops, sorry, I wrote this backwards, R of x over W of x. R of x over W of x. So R of x is e to the x plus e to the 2x times e to the minus 2x over the Wronskian, which is minus 3 e to the minus x dx. So this is equal to minus times minus is plus 1/3 the integral of e to the minus 2x times e to the x is e to the minus x over e to the minus x is 1. And this is 1 over e to the minus x plus e to the x dx. So when I integrate, I get 1/3 x plus e to the x. That's T1. T2 is the integral of v1 of x, R of x over W of x dx. V1 is e to the x. R of x is e to the x plus e to the 2x over W of x, which is minus 3 e to the minus x. So this is minus a third the integral of e to the 3x. This is e to the 2x over times e to the x is e to the 3x, e to the 4x. So this is equal to minus a third e to the 3x over 3 plus e to the 4x over 4. So a particular solution of the non-homogeneous equation y double prime plus y prime minus 2y equals e to the x plus e to the 2x is y1 equals t1 of x v1 of x plus t2 of x v2 of x. So what was t1? 1/3 x plus e to the x times v1, which is e to the x, plus t2, here's t2, minus 1/9 e to the 3x minus 1/12 e to the 4x. I'll just write this as so it's minus 1/3 this times v2 of x, which is e to the minus 2x. So when I put all this together, let's see what I get. I get 1/3 x e to the x plus 1/3 e to the 2x minus, this is a 3 and a 4, minus 1/9 e to the 3x times e to the minus 2x, which makes this minus 1/9 e to the x minus 1/12 e to the 4x times e to the 2x is e to the 2x. And a third minus a 12th is a fourth. So this looks like 1/3 x e to the x plus 1/4 e to the 2x minus 1/9 e to the x. So that's a particular solution of the non-homogeneous equation. And we add that to the general solution of the homogeneous equation. And we're done. Okay. Other questions to do? So our first exam is 1 week from today. It really is an hour exam, but you'll have 2 hours to take it from 11 to 1. The way it works is I will, a few minutes before 11, I will post the exam on the assignment section of Blackboard, the Blackboard website for the class, where you turn in the assignments. And I will also email you the exam. And you'll have up until 1 o'clock, from 11 to 1. So given the computing issues and scanning a paper and turning it into a PDF file or whatever else you might be able to do, there's some extra time, and you'll turn in the exam. What you have to show is your work for all the problems, not just the solution to the problem. If you just write down the answer to the question, you don't get any credit, because I really need to see what you're doing. The rule is that it's an open book exam. You can use your textbook, but you cannot use a calculator or a computer. And you certainly cannot talk to each other while you're taking the exam and do things together. If it becomes apparent somehow that you cheated on the exam, then you get a 0 on the exam. That's standard college and department policy. Monday is a holiday, there's no class. But I do want to make it possible for you to meet with me online if you have questions that come up while you're studying for the exam. So I will post several Zoom office hours when I will be online. And if you have questions, you're more than welcome to log on and ask me your questions. Because there really is this very long gap of a week between today and the next class. How many questions? 5 or 6 questions, but I always put on a couple of extra additional questions for extra credit. So, so you can do better. I mean, the review for the exam is just to go over the homework problems, basically, because what we're doing in this part of the course is just learning some basic techniques for solving ordinary differential equations. I mean, and when we start up again in a week and a half, 2 weeks basically, we'll be going back to partial differential equations. But you can't solve PDEs if you cannot solve ODEs. So that's what we're doing here. The exam will be like the homework, except that I'm not going to give you any problems where, in addition to solving the differential equation, you have to do a huge amount of algebraic stuff. So, so it's basically, here's a differential equation, solve it, or here's a problem about simple harmonic oscillators, and here's the differential equation, solve the problem, whatever it is. So there will be some problems like the applications of first and second order equations, but they're not going to involve a lot of calculation. That's not fair for an exam. We really only have an hour and a half or so to work on the problems. I really want to make sure that you've mastered these techniques for solving ordinary differential equations. I know most of you have not taken an ordinary differential equations class before this, and that's one reason why I have to go through this material. All right, well, if there are no other questions, then I guess we'll stop for today. If you think of a question in the next 45 minutes, I do have an office hour today, as I do every Monday and Wednesday at 1 o'clock. And I'd email, and you'll find on the website for the class, the Zoom login for the office hour, which is different from the Zoom login for the class. So you can just come back then and ask me.
Okay.
Okay, well, if there's nothing else, then study hard, do well on the exam. Have a good weekend also. All right, bye everybody.
Thank you. Take care.
Thank you, appreciate it.
Yeah.